So this is very related work. It's basically work that uses neural networks and similar neural networks, and it's on the exact same task. So it's kind of an extension of what I just talked about. But here we're using neural networks that have a kind of explicitly built-in mechanism for cognitive control with gating. And we're using this mechanism to test the interaction between cognitive control and learning in continual learning or an environment where trials are blocked over time rather than just randomly interleaved. So it's the same collaborators and everything. So in the previous talk, I emphasized how cognitive control could be used to select the currently relevant dimensions, either in the real world in some spatial domain or in internal representations. And but here I want to emphasize how a different aspect of being goal-directed, which is that when you're goal-directed, we often work toward a single goal for an extended period of time. And this has the effect of essentially correlating our learning experiences over time. So for example, you might be wandering around, exploring one part of an environment for an extended period of time, or wandering around a different part of the environment. And similarly, you might be focusing on one of the two dimensions of a social hierarchy, like learning about all the popularity of these different people for an extended period of time. So this may seem trivial that we do kind of one thing at a time in real life often, but for neural networks, as many of you probably know, this can be a catastrophic problem because neural networks are prone to forgetting what they learned previously when their experience is correlated over time. So if you take a neural network, you plop it down in one part of an environment and you train it there for a while, and then you train it in some other part of the environment, it's going to forget a lot of what happened in that first block of training. So a lot of work has been done on this, and there's many kind of proposed solutions to it. But it remains true that humans, it's well established that humans don't suffer from this catastrophic forgetting phenomenon as badly as kind of standard neural networks do. And it's even the case that humans in some scenarios learn better when similar experiences are grouped in time. So for example, the work of Timo Flesch and Chris Summerfield's lab has recently shown that in a very similar kind of setup as the one shown here that I talked about last time, in that setup, humans do learn better when they're learning one dimension at a time, rather than if you randomly interleave the two contexts. And so this is the main kind of target phenomenon that we'll be exploring in this work. But I just want to give a little more background on catastrophic forgetting. So complementary learning systems theory emphasizes that catastrophic forgetting or catastrophic interference happens because representations are distributed, which means that they'll have overlap between different contexts. So if we imagine a single neural network in two different contexts here, the blue context with some hidden state and the red context with some hidden state, and that these patterns are distributed, so there's going to be overlap between them, then when trials are blocked, certain weights will be involved in learning about both of the two contexts, because again, there's this overlap. So if the network were to see for an extended period be learning about the blue context, these weights would be learning about the blue context. And then when the red context happens in the second block, these same weights, or many of them, would be learning about the red context, thereby kind of overwriting what they had learned in the blue context. So this is kind of some intuition for why catastrophic forgetting happens when you have distributed representations, is that when there's overlap, there's interference and there's overwriting of the weights. So in this work, we explore the use of an explicitly defined cognitive control mechanism for inducing a separation between representations across contexts. And this again goes back to this classic computational work, Miller and Cohen, and also some more recent work exploring similar ideas, Sebastian Muselik. And so if we take our network and we add some prefrontal cortex or cognitive control module, which will determine which neurons are active in each context, then if those neurons are kind of separate sets so that there's less overlap, then the idea is that we'll get less interference. So again, when the trials are blocked now, these weights can be learning about the blue context, and a different set of weights will be learning about the red context. And so when you don't have overlap, you don't have interference, and you won't have forgetting. So that kind of explains one way in which blocking might not be as bad as interleaving, might not be worse than interleaving. You can get blocking to be just as good as interleaving, but why would, as I discussed before, why would humans be better when this blocking, when trials are blocked rather than interleaved? So here our idea is that relatedly, the prefrontal cortex is known to have an internal bias for actively maintaining information over time. The prefrontal cortex is known to be involved in working memory and planning, and prefrontal cortex neurons have been shown to actively maintain information over time relative to other brain areas. And so the idea here is that this active maintenance might engender a cost to switching too often. This is another phenomenon that has been well studied in neuroscience and psychology. But for our purposes, if the cognitive controller, the prefrontal cortex, has an internal bias to actively maintain information over time, that might create a cost to switching, which would be, in the blocked case, not so bad because there's really only one switch. But in the interleaved case, where there's many switches between contexts, you might get some interference in the control signal itself, which would lead to kind of worse learning. So overall, our framework then is that catastrophic forgetting happens when patterns are not separated enough. This separation may be induced by a cognitive controller, and this would mitigate forgetting. Furthermore, if this cognitive controller has an internal bias to actively maintain information over time, that would create or engender a switch cost, which would in turn lead to an advantage to blocking over interleaving. Again, because the blocked, when trials are blocked, there's not so many switches. When the trials are interleaved, there are many switches. And we think this also makes sense with some prior work suggesting a trade-off between the degree to which, or the strength of your control signal, and the degree to which the active maintenance causes a cost to switching. So we also have a simulation about that. So in general, we train neural networks on the same social hierarchy task I talked about last time, Park et al. 2020, except now we have two different conditions: a blocked condition where trials are correlated over time, or an interleaved condition where they're randomly sampled. So here's the task again. I won't go into detail this time. Just recall that the network has to learn through pairwise comparisons who ranks higher in one of two contexts on each trial. What I didn't mention was that in all those simulations I discussed before, the trials were interleaved, so they were randomly shuffled, just because we didn't want to deal with this catastrophic forgetting problem, basically. But in reality, with the humans, what they actually did was they had a blocked design where they learned about one of the two contexts first, and this was actually separated over days. So on one day, they just trained on one dimension. On the next day, they just trained on the other dimension, and then on the third day, they integrated the two. But also, Alex and Iri told us that they tried in a pilot experiment to do interleaved for the training, and they found that the participants just couldn't learn as well as when trials were blocked. So that's kind of why they had this block design, and that's consistent with those previous findings that I was discussing before. Timo Flesch and Chris Summerfield about the fact that humans learn better in certain scenarios when trials are blocked. So here's our model. It's slightly simpler in some ways. We kind of ditched the recurrent in the LSTM just to simplify things, because now we have this cognitive controller, this prefrontal cortex module, which controls a hidden layer of a feed-forward network with a simple gating mechanism. Basically, the control signal it produces is just a vector of zeros and ones, or numbers between 0 and 1, that will have a multiplicative, or just be element-wise multiplied with the hidden state. So basically, the prefrontal cortex has control over, which neurons are active in which context, essentially. And we also introduced this lambda parameter for the active maintenance, where a higher lambda means that the control signal is more influenced by the previous control signal. So high lambda means strong active maintenance, more kind of propagation of the control signal through time, and low lambda means less active maintenance. And then finally, we have a gamma parameter that we introduced, which determines the control strength, basically how close the numbers are when they're to 1. So big gamma means numbers are closer to 1. Small gamma means numbers are closer to 0 in this gating layer. So, and that was to test this idea that there's a trade-off between control strength and the switch cost due to the active maintenance. So here are the results. Here we just reproduce the classic catastrophic forgetting phenomenon. So here I'm plotting on the y-axis the accuracy on the task, and this is split into the two contexts. So the accuracy on the popularity trials, the accuracy on the competence trials. So you can see that when the trials are interleaved, the model learns perfectly fine, no forgetting. When the trials are blocked, at first it learns the popularity, and then as it learns the competence in the competence block, it has the performance on the popularity trials degrades. So that's the classic catastrophic forgetting. So when we introduce the prefrontal cortex module, which has this gating, which induces a separation between the two contexts, then we show that this catastrophic forgetting is mitigated, where now when trials are blocked, you can see as it's learning the competence trials, the popularity accuracy is maintained. And then when we introduce this recurrence, or this active maintenance over time, so we increase lambda here, when trials are blocked, it's no big deal, because again, there's very few switches. So the switch cost associated with this increased active maintenance is not so bad when there's not so many switches. But when trials are interleaved and there are many switches, you get this kind of degradation in performance over the course of training, because there's this interference in the control signal due to all the switching happening. And that kind of explains, or is one explanation for why humans might be better when trials are blocked rather than interleaved. And finally, we show that there is a trade-off in principle between the strength of the control signal and this switch cost. So when we reduce the strength of the control signal by lowering this parameter value gamma, we can recover the performance. So basically, if you don't have enough control, you might get some catastrophic forgetting due to lack of separation. But if you have too much control, you get this this interference and degradation in performance when trials are interleaved. But you can reduce that with the getting the right level of control strength. Okay, so we investigated using a neural network with a explicit mechanism for cognitive control with multiplicative gating in a continual learning environment. We show the classic catastrophic forgetting phenomenon. We show that this gating mechanism can mitigate catastrophic forgetting, and then we have an explanation for why humans might learn better when trials are blocked because of the internal bias for the prefrontal cortex to actively maintain information over time, which engenders a switch cost. And finally, we show a trade-off between the strength of control and the extent to which this switch cost hurts performance. Okay, so thanks to all the same people, and I'll take other questions if there are any in this work.
Hello. Very interesting work. So, a couple things in the continual learning literature. A couple of years ago, I was curious to know how you'd compare, for example, Aurora et al. Proposed a model that was very similar using gating mechanisms. Of course, their inspiration was the basal ganglia as an information routing model. So I was curious to know how, for example, it might contrast and how your task might compare when you scale up the tasks, because the continual learning literature looks at very big data sets as well. And while this is very interesting, I don't know how the PFC module that you have, would you speculate would work in that, and how it compares to like a basal ganglia driven lateral context model. The other one is the design of the PFC as well. So again, how do you prevent forgetting, as again in Roby et al., the problem is when you design another module to mediate or gate the original model, like a classifier or a generative model, it itself has forgetting. And so forgetting kind of sneaks its way into the other modules. So how did the PFC itself not catastrophically forget, or is it not learned? Is it programmed in a very particular way? And how that might, again, relate to Aurora et al. 19, and how what you might, for example, adapt it to learn dynamically and also prevent itself from catastrophically forgetting how to gate and learn task contexts. I was curious to know your thoughts and relationships in that.
Yeah, great question. So basically, this setup is not exactly meant to be kind of competitive on a large scale. So I would say that we haven't tested it in larger scales, but I expect that our particular setup is pretty specific to this context, because we're just trying to kind of evaluate in terms of explaining this phenomenon of why humans would perform better in certain when trials are blocked rather than interleaved. So that was our main focus. But I think it's kind of like, no matter what the solution to catastrophic forgetting is, it always looks something like this, where like you basically want to separate the representations for the different contexts that are being blocked over time, right? And so if you can do that, there's various ways of setting that up. But the other part of your question about how you avoid forgetting in the PFC module. So here we kind of punted on that, because we just kind of hand code, like we only have two contexts, right? And the contexts are easily dissociable because we know, which one's which, essentially. So it's harder in the real world, where you have to kind of determine, where it's harder to determine in advance what constitutes a single context, and how you should separate your representations, basically. And so here we kind of just hard coded into the model, hey, if it's this context, some neurons should be active. If it's the other context, the other neurons should be active, just to show this general principle that we're trying to relate to the human behavioral data. But we do have some ideas about having learning in the prefrontal cortex. So I haven't gotten this to work yet, but you could just try back propagating through to see if that helps. I also have an idea maybe about trying to learn it with meta learning objective, where basically the prefrontal cortex learns to optimize the separations such that the feed forward network can perform well on the task, can learn the task more easily, I guess. So that's why it's a meta learning objective. But I would also refer you to the recent work of Timo Flesch, because they have learning in their sort of controller as well, which is a kind of Hebbian rule, which kind of factorizes the two dimensions of their 2D structure in advance. So yeah, sorry, long answer. I hope that helps.
No, very good. And then I also would add then to your future investigation to also investigate Aurora 2019, because they also came up with a
Sure.
mechanism using competitive learning, and that also might be useful in the PFC. It actually turns out to work pretty well when you need a fast controller for a wide set of tasks. So that might be another thing to augment with your meta learning, maybe potential approach too. So be interesting.
Yeah, awesome. Great. Yeah, I'll check it
Thank
out.
you.
Hi, thank you for the talk. Very interesting work. I was wondering about how the network size in your case would scale with the number of contexts that you might want to store in the network. So, for instance, given a particular network, you have an upper bound on the total information that you can store, and you're suggesting separation of representations across contexts. So I'm wondering how your network size would scale with the number of contexts you might store in
Yeah,
a more
that's a great
general
point.
setup.
Sorry. Yeah, great point. So, yeah, basically, I'm kind of hiding that under the rug, I guess, in a sense, because really, I'm just saying that the separation should occur between the two contexts. In this case, we only have two, so it's easy, and we can just have like as many hidden units as we want. But in reality, one way of thinking about what we're doing is that we're kind of just separating the network. We're allocating one portion of the network to one context and another portion to another context. So as you scale up with the number of contexts, you're going to need more and more portions of the network allocated. So they'll be smaller and smaller, or you'll have to make the network bigger and bigger. So I think that is, in principle, a limit to this, how this network could be scaled up. But on the other hand, I don't know if there's like that might just be a fundamental trade-off that you have to make, essentially, is like, yeah, if you didn't have this kind of separation between representations, you'd have more capacity for each individual task, but you'd also suffer from catastrophic forgetting because you're not separating representations, and you wouldn't be able to control your attention. So separation can also be more efficient in some ways. So yeah, I think there's just a fundamental trade-off between the portion of the network that you're allowed to allocate to each task, and these things about separation and what that can get you, if that makes sense. But it's a great point that I probably should have emphasized.
Thank you.
Thank you, Jake. So we're going to move on now to Michael Furlong.